This is section 2.8, derivatives. Our first objective is to work with the definition of the derivative of a function f at a number a to find f prime of a. And when we're done, we should be able to write two different synonyms and two different notations for the derivative of a function f at x equals a. So first, we will notice that this content objective involves a new notation that we haven't seen before, and it also involves a new vocabulary term, the derivative and this f prime of a. So if we read this vocabulary, it says the derivative of a function f at a number a, denoted by this notation, is either the limit as h approaches 0 of f of a plus h minus f of a over h, or it can be the limit as x approaches a of f of x minus f of a over x minus a, provided either of those limits exist. Now, do we recognize this? Hopefully you have a resounding yes to that question, because this is the tangent slope that we've been working with. It also could be the instantaneous velocity that we've been working with, or pretty much any instantaneous rate of change. But what's nice is that now we're going to start thinking about this tangent slope in the context of outputs versus slopes so that we can start to compare them. So with example 1, it says we want to arrange these following numbers in increasing order and then explain our reasoning. So if we think graphically about what these are each representing, we can see that g of 2 is the output, which is actually going to be 0 on this graph. We can see g prime of negative 2 is the slope here at negative 2, and that is a positive number. We can see g prime of 0 is the slope here, which looks like it would be a negative number. And we can see that g prime of regular 2 is the tangent slope here at regular 2, which is positive. Well, looking at these options, our goal is to get them in order by smallest to largest, so increasing order. So we can see that the smallest number in this loop, or in this group, is the negative one. So g prime of 0 would be our smallest. That in turn will be smaller than the 0, which is g of 2. And then we have these two positive numbers that we need to be able to compare. Looking at the slopes, we can see that this slope here is steeper than this slope here. So the slope at 2, or g prime of 2, is actually a smaller number than the slope at negative 2. So we'll put g prime of 2 next, which in turn will be less than that g prime of negative 2. With example 2, we want to find f prime of a for each of these. And the first one, if we want f prime of a, I'm going to keep us in the pattern of where we do the h version, though either one would work. The h version tends to be a little simpler when it comes to factoring at the end. So this will be f of a plus h minus f of a divided by h. Then we can't plug h equals 0 in, so we have to somehow create a top that has a factor of h in it. We're going to get there by replacing x's with a plus h's. So we'll have an a plus h quantity squared minus a 7 times an a plus h plus a 3. Notice that this whole thing is our f of a plus h. Now we're going to subtract this with an a plugged in, and we've got to remember to put parentheses around it, because if we don't, we will neglect the distribution of this negative and we'll end up getting the wrong answer. Our a's won't cancel out. We'll have stuff up there that doesn't have h's in it. So if we look at this now, in order to do the next step, we need to simplify the top. So we've got to multiply everything out and combine our like terms. So I have an a squared plus a 2ah plus an h squared minus a 7a minus a 7h plus a 3, and now I'm going to distribute that negative. So I have a negative a squared plus a 7a minus a 3. That's all over h, and remember that if we do our algebra properly, everything that doesn't have an h in it should disappear. So the a squareds will cancel, the 7a's will cancel, and the 3's will cancel. Now we're left with something on the top that has a common factor of h in it. So I can pull that h out, and I'm left with a 2a plus an h minus a 7, and on the bottom I'll have an h. So now those h's will cancel, and I can compute the limit because h equaling 0 is no longer a problem. plug h equals 0, I get a 2a minus a 7 is going to be my f prime of a for all values of a. If we now move to part 2, or part B, I should say, of that same example, we have yet another function, only this time it involves t's and a fraction. So this one's going to be algebraically a little more challenging. Again, we'll be looking at that limit as h approaches 0 of f of a plus h minus f of a all over h. And when I replace t's with a plus h's, that first one will be a 2 times an a plus h plus a 1 over an a plus h plus a 3. Notice that this expression is the output of the function when I plugged an a plus h in. Now I need to subtract the output of the function when I plug an a in, and then I need to divide by h. Looking at this, it's kind of messy, so we got to remember what we did before, and that is we're going to get rid of the complex fraction by multiplying by the reciprocal of that h on the bottom. Dividing by h is the same as multiplying by its reciprocal, and then I'm going to multiply this through so that we get a nice pretty fraction. Well, actually it's not that pretty. And I'm going to leave some space here because I know I can't get those fractions together until they have the same denominator. So I have to choose expressions that equal 1 that will insert the same denominator. So with this one, I can see that the factor that this fraction is missing is the a plus 3. So I'm going to multiply this one by an a plus 3 over an a plus 3. And this one here is missing the a plus h plus 3. So I'll do that on top and bottom for both. So now that I'm here, I'm ready to multiply out, because remember the goal is to get rid of that factor of h on the bottom that we don't like. So if I distribute, I'll do the 2a times both of these. That gives me a 2a squared plus a 2a times a 3. So let's just make that a 6a. Now I'm going to move to the 2h and multiply that by both. So that's a 2ah plus a 6h. Then I'm going to multiply the 1 by both. So that's an a plus a 3. So I've distributed these two. Now I'm going to subtract what comes out when I distribute the 2a plus 1 to those. So 2a times all three of these will give me a 2a squared plus a 2ah plus a 6a. And the 1 distributed to all three is an a and an h and a 3. Notice that I didn't try to distribute that negative at the same time, because that would tend to make things a little more dicey. I'm more apt to make a stupid mistake. And my denominators, when I combine my fractions, I get each factor only one time instead of twice. So now let's look at the top. Hopefully if we did this right, everything that doesn't have an h in it should disappear. So I've got a 2a squared, I've got a 6a, I've got a 2ah, that actually disappears as well. I've got an a, and I've got a 3. So what's left is a 6h minus a 1h. That gives me a 5h. And on the bottom, I still have my 3 factors. Now notice, the whole reason we went through this process was to get rid of that factor of h on the bottom that was causing us grief. And we've now done that. So now h equaling 0 is no longer a problem, and I can get 5 over an a plus 3 times another a plus 3 gives me a 5 over a plus 3 squared. This will be the derivative at any value of a. You'll notice with part C that I just keep hitting you with algebra. I want you to be able to compute these derivatives, whether you've got roots or you've got fractions or you've got polynomials. I want you to be able to find those limits. So as h approaches 0, we have f of a plus h minus f of a all over h. Now this is going to mix the fraction nightmare along with the radical nightmare. You got to keep both of them, so lots of stuff to keep straight in here. First, we're going to plug in a plus h and see what comes out. So everywhere that there's an x, I'm going to write an a plus an h. Then I'm going to subtract what comes out when I plug in an a. So again, everywhere that there's an x, I'm now going to replace it with an a. And on the bottom, I will put that h. Here we see I've got a complex fraction and I've got some radicals. So we get to pick, and I'm going to tell you it's a little more, or I should say a little less error prone if you choose to get rid of that denominator by multiplying by a reciprocal first. So I'm going to put this division by h as a 1 over h multiplier out at the back, and then I'm going to see here that I have that same common denominator issue coming up. So I'm going to make smart choices for 1 so that I create the same denominator for both of these terms. This one's missing the a plus the h plus the 2. So notice that I chose whatever factor was missing to create that common denominator, and that's smart choice for 1. So if I continue with this problem, I have a limit as h approaches 0 of a root a plus 2 minus a root a plus h plus 2 all over, I've got those 3 roots. So an a plus h plus 2 and an a plus 2 and an h. Well, I still haven't fixed the problem. I'm at least to the point now where I've only got one fraction instead of a complex fraction, and I don't have 2 fractions, I've just got 1, but I still can't get rid of this h because the h's here are trapped. So to fix this top so that I can get this h out of it, because I need to be able to cancel, I'm going to again make another smart choice for 1, and this time it's going to be the conjugate. So I'll take the root a plus 2 plus that root of a plus h plus 2. Same on the top and bottom, because remember I can't alter the value of any given expression. All I can do is alter the way that it looks. So by multiplying by 1, I change the way it looks, and hopefully the new way that it looks will enable me to reduce. So, beauty of conjugates and radicals is that when I multiply a root times a root, just the innards come out. And conjugates, those in between, the insides and the outside multiples are going to cancel each other, so I'll just subtract what's in that last root. And the bottom, because my goal is to eventually cancel this h, I'm not going to, sorry, that's the times. I'm not going to multiply this out. I'm just going to leave it as is. So I have a root a plus h plus 2. I have a root a plus 2. I have an h. And then I have this ugly conjugate still down there. So my bottom's looking worse and worse and worse, but the top is showing some progress. So if I look at the top of this fraction here, I can see that the things that don't have x's in them are going, or excuse me, the things that don't have h's in them are going to disappear. The a disappears and the 2's disappear. So I'm left with a negative h, and it's over h. So I can cancel that h out and just be left with a negative 1. So by the time I have reduced and factored and done all of this nightmarishly long algebra, I'll end up with a negative 1 over that big mess on the bottom. But what's nice about that big mess on the bottom is that it does not have an h as a factor. So I can plug in an h equals 0 now and compute the limit. So if I do that, all of these h's are going to turn into zeros, and I'll get a negative 1 over an a plus 2 in a root, and another a plus 2 in a root, and then I'm going to have 2 of those a plus 2's in a root. So some people get a little mixed up in simplifying this, and I'm going to tell you the answer that you would see on a test from me would be 2 of these a plus 2's raised to the 3/2. So let's talk about where this 3/2 comes from. Remember, radicals are the same as a power of 1/2. And when you repeat the base, you're going to add exponents. So I have an exponent of a half, another exponent of a half, and a third exponent of a half. If I add those halves together, I end up with a 3/2. So here is my f prime of a, and I'm done with the worst example you'll have of this to date. Okay, once we get comfortable, or at least a little better at computing these derivatives, I will start to ask you to go backwards. So now, instead of asking you to compute the limit and find the derivative, I'm going to give you something that represents the derivative and ask you to figure out where it comes from. So in order to do this, we have to recall that we've got two ways to write that derivative. We can have f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a over h, or we can have the other version, which is the limit as x approaches a of f of x minus f of a over x minus a. So we were given those limits, and we want to come up with the function and the a. So first thing we're going to do is we're going to look at the limit piece of it, because that'll help us figure out which format of the derivative we're actually working with. And I can see here that these are both h's approaching 0. So that's going to be my first one, or the red one. In order to compute this limit, I need to know what my a is, and we can see that the a is right here and right here. So we've already got the a's figured out. The second thing we have to figure out is the function itself. So the function itself, right here, this first term, has an a plus h plugged into the function. So if we change that a plus h to an x, we should be able to find the function itself. So if I change this 1 plus h to an x, we can see that the function is going to be x raised to the 10th. Same thing here. If I replace this pi plus h, that's my a plus h, and I put that inside the first term that we see in the difference quotient, we can see that the function in this one is actually the cosine of x. So now let's look at the third and final, number 2, which is the green version. This one has an x approaching a, so we can see that x is approaching 5. This one's actually much simpler because it's easy to read the a off. It's just whatever x is getting close to. And it's easy to read the function because that is the f of x on the top of your fraction. So in this case, f of x is 2 to the x. Okay, with example 4, our algebra tools are not going to work for us, so we have to work a little differently and think about what it means to actually have a tangent line. Remember way back in section 2.1, if I had a function and I nailed down a point and then I dragged another point onto that point, the original one, I ended up getting a series of secant lines whose limit became the tangent line. So what this means for us is that graphically, as we drag these points closer and closer and closer to each other, we should end up getting a curve that matches up pretty closely to the tangent line. If I zoom in close on a tangent line, the difference between this point and the y-coordinates on the tangent line and the curve is pretty small if I'm close enough to that point. So we're going to use that fact to look at both of these, which are problematic at 0, because when I plug 0 in, I've got a division by 0 inside a trig. So there should be some sort of oscillation going on, and we just have to figure out whether the oscillation is too much or if it gets dampened out and actually works for us. So we're going to look at these on our calculator as opposed to looking at them analytically. On the calculator, you can see that I have entered y1 and I've entered y2. y1 is this x times the sign, and y2 is x squared times the sign. And what I'm going to warn you about on the calculator is that if you do not insert the time symbol, your calculator will think you have a function called x sign and nothing will graph, because you don't have a function called x sign assigned in the memory of your calculator and it won't know what to do. So you'll either get errors or it'll just be blank. So for right now we have this x times the sine of 1 over x, and then we have x squared times the sine of 1 over x. And I want to start out looking at the second one. So that means I'm going to turn this first one off so that we're only graphing the second one. Notice that both of them right now have have little check marks on them. So to turn off that check mark, I'm going to use F4, and then I'm going to look just at the function x squared times the sine of 1 over x. So I'm going to go into my window. Actually, let's just do a zoom. And I'm going to zoom standard. We'll start off with that. And here's our function. Looks pretty nice, except maybe we can't really tell what's going on at 0. So if I zoom in at 0, I'm going to notice that I still can't quite tell because I've got the axis in the way. I can't tell what's curve and what's axis. So I'm going to access my F1 option, and there's a format for formatting anything that's going on with the graph. And I'm going to turn off my axes so that all I see is the actual function. So now we have a little more clarity about what's going on near that 0, but still not quite enough. So I'm going to zoom in. And as I'm zooming, let's recall that when we create a tangent line, we want one point at 0, 0, and we don't want another point that's getting close. And we want to connect those, and that'll be a secant line. And then those secant lines, as I drag the points closer and closer, should start narrowing down on a single tangent line. So if I zoom in again, I can start to see that near the origin, things are flattening out pretty nicely. They're starting to look like a line. And now I'm looking even more like a line. Let's go in one more time. If I get close enough to a point of tangency, then the behavior of the curve will be indiscernible from the behavior of the tangent line. They will look exactly the same if you get close enough. And what do you know? Here I've got that curve that looks an awful lot like a line. And that line that it's looking like is the tangent line. So because it has a tangent line and the curve zoomed in looks like a line, we can say that this second one, f prime of 0, exists, and that it equals 0, because that was the slope of the line that it becomes if we zoom in far enough. So this happens because zooming in creates a line. So let's try that same thing with the first one. So back to our calculators, and we're going to go back to our Y editor. This time I'm going to turn off the second one, and I'm going to turn on the first one, and I'll start again with the zoom standard. Well, at first glance, that doesn't look too bad. So we're going to zoom in on that 0, 0 and see. It looks kind of like it might be parabolic in there. Doesn't look as promising as I thought at first glance. If I keep zooming, remember the goal is to make it look like a line. Zoom in again. That is not looking like a line. In fact, what I see on my screen, even though my window is getting closer and closer and closer to the origin, what I'm seeing does not look like a line. In fact, it's getting messier and messier the closer I get. So on this particular version, I would say that f prime of 0 does not exist. And if I go back to my picture and look at it, if I'm trying to create secant lines and then I'm dragging that point closer and closer, notice that the secant lines, they'll go positive slope one time, negative slope, positive slope, negative slope. It's just wildly bouncing all over the place. So that secant line, that series of secant lines is not getting closer and closer to a single tangent line. They're just bouncing everywhere. So again, that f prime of 0 is not going to exist. We're not going to have a tangent line there. So now, based on this example, what do you think the phrase local linearity might have to do with the existence of a derivative? Write that down. Now you should be able to work through your notes web exam problems, and when you're done, I'd like you to write 2 different synonyms and 2 different notations that mean the same thing for the derivative of a function at x equals a.